This is the video for the second part of the circles test for Pre-AP Geometry 2014. We can start with number one. We have a tangent line to a circle. We want to know the slope of OP, which is that line there. To find that slope, we find the triangle. We know that we go down 2 and over 4. Remember, the over 4 is on the bottom. That simplifies to a slope of -1/2. The radius and the tangent line are perpendicular to each other. So if the slope of the tangent line, or sorry, if the slope of the radius is -1/2, the slope of the tangent line is +2/1. We know the point P here. We can write our equation for the line. We have y minus the y coordinate equals the slope x minus the x coordinate. And we solve this for y. And that process will be the same for any line through any tangent point to any circle. Find the slope of the radius to that tangent line. Convert the slope to the perpendicular slope. Use that slope with the given point. These problems here. We want a segment congruent to QS. We know that OS and OA are the same. And since we know that they're the same part of different radii, then the rest of the radii need to be the same too. So AU is congruent to QS. Congruent to QR, the arcs congruent to QR are the ones that have that same central angle. We know that if the radius perpendicularly bisects, well, if radius is perpendicular to an arc or to a chord, it bisects the chord. It also bisects the arc. So PQ or QP is congruent to QR. And then since we know that these chords PR and VW are the same distance away from the center, they make congruent arcs. And VW is also getting cut in half, so each of the halves, VU, sorry, that should be an arc, VU and WU are also congruent to QR. And as I just said, chords that are the same distance away from the center in the same circle are congruent to each other. So PR and VU are equal lengths. For the pentagon, we know that congruent chords make congruent arcs. So all of these arcs are going to be the same as well. 5 arcs together make the 360 degrees. So each arc is 72 degrees, including QR. Angle QTS, or sorry, arc QTS, that goes the other way around because we need to go through T to get there, is 1, 2, 3 of those 72 degree arcs. So this is going to be 72 times 3, which is 216 degrees. And obviously, when I meant QR is congruent to 72, I meant to put a 72 there, not be reflexive. Here, we know the tangent lines from the same point to the same circle are congruent to each other. This is one of those artificial quadratic questions. This is not naturally a quadratic, but this expression makes it so. Whenever you have a quadratic, you want to set it to equal to 0, and then you would like to factor the non-zero side. So we're looking for two things that when you multiply them, you get negative 15, and when you add them, you get negative 2. And those two things are negative 5 and positive 3. We have a multiplication where the product is 0. The only way to get 0 as an answer to a multiplication problem is to have 0 as part of the multiplication problem. So maybe that one's 0. Maybe this one's 0. We're not sure. Let's find out. We add 5 over here, subtract 3 over here. It looks like right now that's not going to be a negative number. We can't have the negative number, but let's just double check because we're not actually solving for a particular length. We're solving for an expression, or the length is the expression. So we could have 5 squared minus 2 times 5 is 25 minus 10 is 15, and that works. That's congruent to this 15 there. Or we could have negative 3 squared minus 2 times negative 3, which is positive 9, negative negative mix plus 6 also equals 15. So while normally we can throw out negative answers, in this case, both of these answers are legitimate. For this one here, I don't think we need this part at all. We have outside times the whole thing, which would be 13 times 13. All it is, remember to go back to the point of intersection, equals 10 times 10 and x. You need to go all the way through the circle to the other side. Six point nine is not a rounded number, so we will accept either answer. Here we have this lovely radius, but it's not where we want it to be. So let's swing this radius up over to here, and that is 7. We'd like to find AB and the measure of arc AB. Well, first of all, let's find half of AB. And we can do that because we know that when a radius bisects a chord, it is a perpendicular bisector of a chord, which means we have a right triangle, which means we can do Pythagorean theorem to find this right here. Keep in mind that the hypotenuse is the one that's on the side by itself. So if this is square root of 33, and this is another square root of 33, because they're congruent, AB equals 2 square roots of 33. Now to find the angle. I'm going to clear some space here, although we still want that radius drawn in. Now we're actually looking for this angle right there to make this arc. So I'm going to call that one Y because I don't want it to be another X. So again, same triangle. We know, we don't know the opposite. Well, we know the opposite. I don't want to use the opposite. It's a square root of 33. We have the hypotenuse and we have the adjacent. So using the adjacent and the hypotenuse means we use cosine. Cosine negative 1 both sides, and my calculator tells me that that is 55.15 degrees. And at 1 decimal place, that's 55.2 degrees. This problem is super duper simple. If the chords are the same distance away from the center, and by distance we mean perpendicular to, then the chords themselves are congruent. So if this chord is 15, this chord is also 15. Here we have a circle. We know that there's a right angle there because the radius meets the tangent line there. we could go all the way through the circle, in which case we would have x times x plus 4 plus 4 equals 10 times 10. But as we'll notice pretty quickly, that gets to be not a terribly fun quadratic to do. So let's try plan B. And instead of doing it that way, use the fact that this is a right angle, and we'll do the Pythagorean theorem. Since this is 4, that's also 4. So that's another radius. I'm just going to call this y for a second, because it's going to make my life a little bit easier. So 4 squared plus 10 squared equals y squared. And all I need to do once I get y is take that 4 back away, and I'll have x. So this is 116 equals y squared, which simplifies, but it's not pretty. This is 2 squared of 29. So if you want it exactly, x is 2 squared of 29, and then subtract 4. If you want a decimal, which I would totally let you do in this case, that would be approximately 6.77 units. Here we have CD is 12, CF is 7, which means that that's 7. We know that these are right angles. We need to know what that side is. This is another Pythagorean theorem problem. Wow, you have lots of Pythagorean theorem problems in here. Yes, be ready for them. So again, I'm just going to draw this out separately so I can see what's going on. The hypotenuse is 12. This is what we want to know. That's our x. So x squared plus 7 squared is 12 squared. Which does not simplify. We have a set of some easy problems mixed in with this first problem, which is not too bad. Again, we're going to do the outside, which is 8, times the whole thing, which is 8 plus 6. Or, if you want to get fancy, 14 equals 4 times all the way back to the beginning, 4 and x. Number 12. You probably did that problem and said, oh, that looks like it's probably a typo. Guess what? It is a typo. This is 7. Yay. This is x. This is 3. And we want to know what this is. Oh, sorry, that's also 3. Super duper easy problem. 3 plus 3 is 6. Just because it looks hard doesn't mean it is hard. It looks like a square. We know these are right angles because their tangent lines meet radius. We know that these are the same because they're both radii. So it's a rectangle. It's also a kite because these two sides are the same and these two sides tangent lines to the same point are the same. A rectangle that is also a kite is called a square. So all 4 sides are the same, and x equals 11. With the perimeter of this triangle, keep in mind tangent lines from the same point to the same line, or to the same circle rather, are the same, so that's 8. That's 10. That's 10. This whole thing was 16, so that's 6. So that's 6. And we have every piece of the perimeter. Personally, I would say that we have 2 10s, and 2 6s, and 2 8s, which would mean we have 2 of 10 plus 6 plus 8. 10 plus 6 plus 8 is 24. So the perimeter is 48. But if you have a calculator, you could probably do that just as fast, if not faster. Here's this lovely pair of problems that you need to know how to do. First one, with both of them, we need to draw in another radius. Here, if we draw this in, we have a Pythagorean theorem problem where we have x squared plus 25 squared equals 20 plus x squared, which is going to get messy, so let's not do this that way, because that is the bad way of doing that problem. And by bad, I mean it takes a lot longer than you'd want it to. So let's instead do the ow. We have the outside times the whole thing. And by whole thing, I mean from this intersection point all the way through the circle, which means it's not just 20 plus x, because we have another x here. So it's 20 plus x, or 20 plus 2x. And on the other side, 25 times 25. This one, by contrast, if we try to do the same way, we do x times x plus 5 equals 15 squared, we end up with a quadratic. And if we can avoid doing a quadratic, I would rather avoid doing a quadratic. So this one, let's drop this radius to the tangent line, and now you go, it's a Pythagorean theorem problem. And again, let's call this y just for now, and we'll subtract 5 from y, and we'll get x. So we have 5 squared plus 13 squared equals y squared. If you recognize your triples, this is not one of them. So we have y squared equals 194. Y equals approximately 13.92838828. And because we want x and not y, we're going to take out the 5. So x is approximately equal to, not congruent to, 8.93. This problem here, we have 2 different relationships that we need to make work. We have the fact that we know that this perpendicular means that the whole chord is twice as long as this part, which means we need to find numbers that are doubled. So the only numbers that are doubled are the 5 and the 10. So this one has to be 5. This one has to be 10. The other piece of this is we have a right triangle, which means we need to have a Pythagorean triple. We're looking for a Pythagorean triple that has a 5 in it. So if you go down your list in your head of Pythagorean triples that have 5 in it, you come across 3, 4, 5. And you're like, oh, great, 3, 4, 5. That's wonderful. Except 5 is the hypotenuse. And 5 is not the hypotenuse here, so that doesn't work. So neither does this. So you go to your next triple, which is 5, 12, 13. And you go, oh, 5 is now a side and not the hypotenuse. So the other 2 sides have to be 12 and 13. This is a basic problem. We're going to intersection to the circle, x times intersection to circle, 6, along the same line. Other one, 4 times 8. these two products are equal to each other. We have 6x equals 32. Divide by 6, and we get x equals 16/3. Same exact setup here, except we now have to find AD. But we are going to go from intersection to the edge. Let's put the information in first, shall we? That was easy. So then we have intersection to the edge, x plus 3, times intersection to the edge along the same line, times 9, equals, on the other, 5 times 2x minus 1. There's no adding to do in these problems. These come from proportions. The addition comes in when you are outside the circle and you need to go to the circle. This one is just straight up multiplication. And you go back and read the problem, and you go, oh, we weren't asked for x, we were asked for AD. So this thing here then is 2 times 32 minus 1, which is 63. And then this part is 5, so this is 68. Here again, we do need to do some addition. We have 8 times 8. And on this one, we have 6 times 6 and x. And these are equal to each other. Here, when it's outside the circle, you do need to make sure that you add all the way through from the intersection to the other side of the circle, which is why there is this addition sign right here. If I did that correctly, that would be 14/3. Same thing on this problem. We have x times x for that line, and 6 times 6 and 9 for that problem. These are equal to each other. X squared equals 6 times 9 is 15. 6 times 15 is 90. X squared is 90. We can simplify that. 90 is 30 times 3, or 3 times 3 times 10, which means we have a pair of 3's that come out and the 10 that does not. Even though that's 2 times 5, that's not going to find any more pairs for us. Here we need to draw a circle first, and we need to draw a chord. This chord, 46 inches. This arc, 94 degrees. We need to draw a radius here and a radius here. This radius connects the center to the end of the chord. This radius is perpendicular to the chord and therefore bisects it. So that means that this half of the chord right here is 23 inches. And since it also bisects the arc, each half of this arc is 47 degrees. And if the arc is 47 degrees, the angle is 47 degrees, which means I want to see this triangle a little bit bigger. So I can do that. We're being asked for the radius. The radius here is the hypotenuse of this triangle, which means this is a very basic trig question with a little bit of circle knowledge thrown in there. From the 47 degrees, we have the opposite. We would like to know the hypotenuse, but we're going to use sine. Because the r is on the bottom, we need to cross multiply that up. And we are going to cross divide the sine of 47 degrees. So you have r equals 23 divided by the sine of 47, which your calculator should tell you is about 31.45 inches. Radius of the big circle is 8. Radius of the small circle is 4. That's a tangent line to a radius, so that is a right angle. So we have this triangle here, AEO, which you can Pythagorean theorem and find that third side, or you could recognize, wow, the hypotenuse is twice as long as one of the sides. Where have I seen that before? The answer to which is, oh, that's a 30, 60, 90 triangle. Oh, tricksy, Mr. Long. Very, very tricksy. So we know this is 4 squared root of 3, which means this whole side, and thus that side would be 8 squared root of 3. And the area of the rectangle is going to be the length times the width for part B, which is 4 times 8 squared root of 3. But that's not really a rectangle. It's a rectangle with the circle cut out. So minus the area of a circle is r squared times pi. If you would like to leave it in perfect answers, it is that if you would like to approximate it as a decimal, it's about 5.16. We know our units. And we're in the second dimension because we're talking about area. Love this problem. The rhombus. A couple ways of doing it. Either way, you need to draw in the diagonals. You also need to know some things about a rhombus, such as the diagonals bisect each other because it's a parallelogram. Also, in a rhombus, the diagonals are perpendicular because it's a kite if you're one of my students. And if you're not one of my students, because it's a rhombus. So if AC is 10, that means that each of these are 5. If BD is 24, each of these are 12. There are 2 methods to do this. And by 2, I mean there are lots of methods. I find these 2 to be the best. The first is we're going to draw the radius there, perpendicular to the tangent line. We need to find this. Regardless of which method we're doing, we need to find that. We go, that's a right triangle with sides 5 and 12. And if you remember back a couple problems, or you Pythagorean theorem, or you just know your Pythagorean triples, we know that each of the sides of the rhombus is 13. So, method number 1. We have this triangle with this radius altitude drawn in there. This triangle is really three similar right triangles. There's the baby right triangle, there's the medium right triangle, and there's the big right triangle. It's like Goldilocks in the 3 triangles. This one is too small. This one is too big, and this one is just right. And I don't mean to pass a value judgment. Any 2 of these triangles work as long as you're using this one here, because that's the one that we know all 3 sides of. So we make a proportion. We say R is to 12 as 5 is to 13. And no matter how you set it up, you're going to end up with something that looks, excuse me, very, very similar to this proportion. Cross multiply up the 5, or the 12 rather, and you get R equals 60 over 13. Method number 2, we're going to use the areas. The area of a rhombus equals the base times the height. In this case, the base is 13, the height is 2 radii. We know that this rhombus is also 4 triangles, 4 right triangles, each of which is half of the base, which is 13. Sorry, the base of the triangle is not 13. The base of the rhombus is 13. The base of the triangle is 12. The altitude of the triangles, if we lay them like we have here, is 5. And because we're talking about the same rhombus, these areas have to be equal to each other. So 26R equals 4 times a half is 2 times 60. And when you divide by 26, you simplify, and you get R equals 60 over 13. So to recap, regardless of how you do this, whichever method you need to use, whichever methods you're going to use, you need to find that. You also need to draw in the radius perpendicular to the tangent line. You can use trig if you forget the proportions to find the angles, to find the missing sides. You're welcome to do that to find R as well. Although, again, these two methods are faster, I believe, and more accurate because you don't have irrational numbers. Number 25. First thing to do is put all the givens in. PR is 18. I'm thinking this is perpendicular. QU is perpendicular to PR. So that means that this 18 is getting cut in half. Each of these are 9. And U is 115 degrees. And QU, the diameter, which means the radius, is 41. And that's the number I care more about. So let me put in the radii here, 41, 41. And NO is also 41, but let's come back to that one. We know that this is a tangent line meeting a radius, so that is 90 degrees. The fact that this arc is 115 degrees makes this angle 115 degrees, which makes this angle 65 degrees. Which means that we can find the other two sides of this right triangle. So to find, or first let's find angle T. Angle T is going to be 90 minus 65, which will be 25 degrees. To find UT, we need to use some trig. We know that this is opposite to this 65-degree angle, and this one is the adjacent, and the one that uses opposite and adjacent is tangent. Tangent of 65 degrees equals UT over 41. Cross multiply the 41, plug it all into the calculator, and you that should be enough. I'm going to carry it to a couple more places outside. find ST, we just need the third side of this triangle. We can Pythagorean theorem with UT if we're feeling confident about that, or we could just do some more trig. This is now the hypotenuse, and by hypotenuse I mean all the way across, and then we will subtract 41 from that. So we're going to use now the adjacent and the hypotenuse, so that is cosine of 65 equals 41 over h. Cross multiply the h up, cross multiply the cosine of 65 down. And you get h is about 97.01. We are then going to subtract the radius from that. So ST by itself is 56.01. We could have done this one by doing ow and going all the way across the circle, but then our variable is on the outside part of that, and that's going to mean we're going to have to do some crazy factoring and or quadratic formula. And I'm guessing that's not what you guys really want to be doing. To find arc QR, we are going to draw that radius in. This radius, like all the radii in this problem, is 41. So now we need to find out what this angle is. I'm going to call that x because I have not used x yet in this problem. And I'm going to clear some space. For this triangle, from x, 9 is the opposite, 41 is the hypotenuse. We're going to use sine inverse sine on both sides. And your calculator will tell you that the angle is about 12.68 degrees. And since the angle is the arc is about 12.7 degrees as well. To find PU, I'm going to erase some of the things in this diagram. I'm going to use this right triangle to find PU. We know this is 41. We're going to need to find this first, aren't we? So on this one, we're going to Pythagorean theorem. Let's call this y for a second. Y squared plus 9 squared equals 41 squared. If you remember your Pythagorean triples or you solve it, you're going to get y equals 40. So in our big triangle here, the long leg of this is 40 plus 41. So the long leg of this will be 81 squared plus 9 squared, which will equal PU squared. PU is about 81.50. QM, very simple. We're just going to subtract this 40 from the full 41 of the radius. 41 minus 40 is 1. We could have done it this way. We could have said QM, I'm going to call that Z, times the other part of that line. Could have done Z times, we just said that was 81, equals 9 times 9, 81z equals 81 will also give us 1. Angle PUQ, this angle right here, we know that this arc is 12.68. And this angle is going to be half the arc because it is inscribed angle. It is on the circle. So that's probably the easiest way to do this, although you could certainly do trig with this triangle, the 9, 81, 81.5 triangle. But again, 12.68 divided by 2, probably the fastest way to go. About 6.3 degrees. Angle OLU. Without knowing the arcs, probably just going to want to use triangles. So let's use this triangle here. We know the 115 degrees. We just found out that was 6.34 degrees. And we subtract those two from 180 degrees. And we're going to have 58.66 degrees. And that is the review. The links for the constructions are below. Good luck.